Hi, today I have a new example to present to you. It's ORTools example number 6, and we're going to conduct a two-stage parent grain reconstruction in a twinning and transformation-induced plasticity steel. So let's have a look at the code. As always, you can find that on the GitHub repository under the examples, and it's number 6. And I'm going to run you through it step by step. So we're going to start with this first section, Control-Shift-Enter. Just to initialize everything. Then we're going to start up MTech, define some of the relative folders, and in this third section here, we're actually going to load the EBSD data that's provided to you in the data folder of ORTools. So just download the entire repository and you should have everything. So then we're going to calculate some grains here of the index EBSD data. We're going to take a threshold for grain construction of 3 degrees. And afterwards, we're going to smooth these grains to make the outlines, the boundaries look a little bit nicer. Then here we can rename the faces. So we have this iron FCC, we're going to call this gamma. We have iron BCC, we're going to call this alpha prime. And we have epsilon martensite, we're going to just call it epsilon. Then we can recall the faces. Let's take something nice. Or maybe it's not so nice, but anyway. So here we plot the phase map. So we can have a look at the microstructure, and I can explain you a little bit what we are dealing with today. So this is the microstructure. Here in purple, we have gamma, which is the parent phase. So that's the phase before any transformation happens. And then we actually have two different transformations that happen. So the first one is epsilon gamma to epsilon transformation. So that's a martensitic transformation, and epsilon is a hexagonal phase. So all these green bands here are hexagonal phase. And furthermore, we have a transformation from epsilon to alpha prime, and alpha prime is a body-centered cubic phase or tetragonal. So these are the yellow phases within epsilon. So we can actually see that there's no alpha prime that actually formed from gamma. So everything goes from gamma to epsilon to alpha prime. And that's exactly the way we're going to reconstruct things today. So in a reverse manner, we're going to reconstruct alpha prime to epsilon and then epsilon to gamma. Let's have a look how we do that. So in the beginning, we have to start setting up and explaining the computer program what the parent phase will be and what the child phase will be. So as I just said, we're going to start by taking epsilon as the parent and taking alpha prime as the child phase. And then we can just, for convenience, plot a inverse pole figure map of both the parent and child phase to have a little bit an idea of the microstructure. We can see here that we have within one of these epsilon bands, we have a lot of different alpha prime colors. Actually, a limited number of colors, but there's different orientations there. And these bands here are all like areas of common orientation. So we want to first, of course, define the orientation relationship. That's not defined yet. And we're going to start by assuming a Burgers orientation relationship. So I can just here mark this and do F9 to execute this command. And then we can use this command plot hist or misfit to show how well actually this orientation relationship represents the misorientations in our microstructure. So here, beware, we have two figures. So one is the parent-child grain disorientation distribution histogram, long title, and one the child-child grain disorientation distribution histogram. So what do we see here? We basically see that the average misfit between the parent-child grain boundaries with the misorientation of the orientation relationship is around maybe, let's say, 2 degrees. So this is the peak here. And for the child-child grain disorientation, so in this case, alpha prime to alpha prime boundaries, it's also around 2 degrees. This peak here at a low disorientation just tells us that we have a pretty good fit between this orientation relationship that we now assigned, this Burgers orientation relationship, with what we actually find in the microstructure. Nevertheless, we can further refine this by using the mtech function calc parent to child. And here we only take the parent to child boundaries to actually refine this orientation relationship. So it will basically, in an iterative manner, get better at the orientation relationship estimate by comparing itself to the parent to child boundaries. And when we do this, we can afterwards again run this histogram command and see if we got any better. So let's have a look. So this was our old misfit. This is the new misfit. Yeah, maybe we got a tiny bit better, but I think not much happened actually by this refinement. So we were already pretty good. But anyway, we have a very good, let's say, foundation to start the reconstruction process. We can also now look in this next section here and run this command plot map GB misfit. This is basically showing the same misfit that we have in histogram, just that it plots this locally onto the grain boundaries. So we can actually see we put this threshold here to 5 degrees for the color scale, and we can see that most of the boundaries have a pretty good agreement with the orientation relationship. So this should be easy sailing for us. What we can do now is we can reconstruct the alpha prime phase by a small loop where we calculate grain boundary votes at parent to child boundaries, and we then calculate the parents from these votes. So since we have most of these grains, most of the child grains are in contact with the parent grain, so that's very easy then to reconstruct these grains because there's already, let's say, only a limited number of orientations as possible, and then by comparing to what's already in the neighborhood, this reconstruction is pretty simple to do. So we run this loop 3 times, and afterwards we're gonna plot the reconstructed epsilon phase. That's what we have here. So now we can see actually these empty spots before where we had alpha prime are now filled with epsilon, and yeah, the orientation fits very well to the surroundings. Now, of course, we have a lot of similar grains next to each other, and we can use this command merge similar here with a threshold of 7.5 degrees to merge all the grains that have very common orientations and are neighboring to each other. So now we actually merged all these alpha prime grains after they've been reconstructed into the pre-existing epsilon grains. So now we actually finished the reconstruction from alpha prime to epsilon. What we now want to do is to do the same thing for this reconstructed epsilon to gamma. So this is done in this section here, and now we again set up the parent grain reconstructor, but instead of providing EBSD and grains, we're now going to use job EBSD and job grains. So these are the already reconstructed EBSD data and already reconstructed grain data from the previous reconstruction. And we're going to then define something called job 2. So this is how we did this before. We had EBSD and grains and defined job. So when we do this, again, we will have to tell MTech or ORTools what the parent phase is. This time we want gamma as the parent phase and epsilon as the child phase. Then the orientation relationship here is initialized as Shoji Nishiyama. And again, we can see whether that's any good by plotting these this orientation diagrams. You can see it's pretty good. Again, like around 2 degrees misfit on average. We can again do this refinement of the orientation relationship and see if we get any better. And actually, even though we were already pretty good, we got even better by refining it. So this is an ideal OR to actually do the reconstruction on. We can again plot the misfit of the grain boundaries at the local grain boundaries. Yeah, we can see that most of the grain boundaries actually have a pretty good fit, especially the parent to child boundaries. Some of the grain boundaries have a fit that's worse than 5 degrees, but we can see later on that this still leads to quite good reconstruction. So here we reconstruct gamma in a loop of 3 iterations. It's the same method, just on the different phase combination this time. And after 3 iterations, we plot the pole figure, the inverse pole figure map, and we can see that we now successfully reconstructed the hexagonal phase to gamma. Again, we want to merge similar grains so that we get a little bit of a nicer image. This is done here, and now we basically have the prior austenite grain boundaries here as well. So I think this is a quite good example of how to do this 2-stage reconstruction. I'm now gonna briefly show you a little bit of analysis you can do. So now we have all this reconstruction information from alpha prime to epsilon in this object job, and we have all the reconstruction information from epsilon to gamma in this object job 2. So we can now use job and job 2 to actually do the post-processing or some analysis on that. So let's start with job 2. So that's the gamma to epsilon transformation. So we can do plot PDF variants. This gives us a pole figure showing the variants. the variance of epsilon with respect to the gamma phase. We can see that we basically have 4, but by a slight misalignment of the orientation relationship with the perfect Burgos OR, actually these split up into 8 variants. Then we can calculate the variance actually for the grains that we have in the microstructure, and then we can plot the variant map. So here we have the outlines of the prior austenite or gamma grain, and in here we can then color all the epsilon phase according to the variant ID. And by comparing to this image, we can then basically identify which variants we are talking about. You can see that, for example, here red is basically one variant that has been split to 2 different variants. If you want this to be called as one variant, you can always redefine the orientation relationship to Burgers again without doing the refinement afterwards, and then you will only have 4 variants in this map. So that's always a way forward if you want a different plot. So now, as I already announced, we can do the same thing for the epsilon to alpha prime transformation. So we can plot the alpha prime variants as a function of, with respect to the epsilon phase. We have 6 different variants, and here some of them, of course, according to the hexagonal symmetry, equivalent to each other, but 6 unique variants. We can again calculate these variants and plot the variant map, this time for all the alpha prime grains in the epsilon phase. So in here we can see this variant coloring as well. So you can basically, by working with job and job2, do analysis on both of these. This is a new function that I have not mentioned in any video yet. It's called save image. It does what you would expect it to do. So you can just call your image test 1, 2, 3, and then it will basically save all the open figures with numbering in the folder of your choice. And by default, that's your ORTools data output images folder. And you can even choose some different image formats. So it's pretty handy if you want to make publication ready figures. Then we have, of course, this function grain click. I've introduced this before, but I want to show it again. I've now actually added a small tool to it, which is no scale bar, no frame. So these are 2 properties, and I will show you now what these do. Grain click will close all your figures. Just beware of that if you want to save them before that. So in this case, we look at the gamma grains, and we're going to do some analysis on the epsilon grains in there. So we can, for example, go for this grain right here. We can see the outline of the gamma grain and the inner boundaries of the epsilon grains. And by clicking on this grain, it will produce a lot of figures. Yeah, as always, now these figures are going to open on the wrong side of my screen, but I'm just going to drag them over and talk a little bit about them. So I already start dragging over some figures. So this here is basically the parent grain, gamma phase, the child grain, epsilon phase in the phase colors. And here we have the parent orientation, and you will see this orientation gradient here. So this material has been deformed, and we could actually recover this deformation in the parent grain. This is the EPSD data we plot, so it's not the average or mean orientation of that grain, but it's the actual local orientation that we recover. And you can always use grain click with the property grains behind that if you want the grain data instead. But usually the EPSD data looks nicer, gives more information, but for a very large data set, of course, it can take a little longer to plot. Then here, this is the the orientation of the epsilon phase. Let me see what else we have. So here are the variant IDs. And this is similar information to what we plotted before, just that here we have the grain of choice. So you can take this figure and just do save as and use it for publications. And this is actually why I personally introduced this no scale bar, no frame, because you often have this kind of boxy frame around it in the scale bar, which sometimes overlaps with your data. And if you, for example, have a nice map that you want to show and just want to highlight one grain, it's nice to be able to get rid of the scale bar and the frame and just be able to copy this grain and put it somewhere into a figure. So these are options you can use. Then we have the packet map. That does not really make too much sense in the in the context of FCC to HCP transformation. But if you define the packets right and you want to kind of look at different habit planes and these things, you are able to use that. But in this case, it doesn't really make any sense. This here is the parent orientation. So these are the orientations of the parent EBSD data. These here are the child grains, the theoretical variants of that. Then we also have the actual variants, so we can actually see which variants have formed. You can see there's a little bit of a spread, but luckily since we have few variants, they were very easy to identify. And we can see that all of the variants have formed in this particular grain. Yeah, there's more things here, but I've already shown some of them in another video, so I'm not going to go too much to detail with it. Here we have the variant fraction. Yeah, these are things you can basically get out of this grain click function. You can also run this with job 1, of course. All right, I hope you like this example and I hope you can use it for your research. And yeah, if you have any feedback, please let me know. And until then, have fun.